Okay, so let's talk about something called electronegativity. So let's define it first. So what electronegativity is it's the ability of an atom to draw an electron to itself within a bond. So at the end of a previous chapter, we talked about some of the periodic trends, electron affinity and ionization energy, which was talking about gaining or losing an electron. The difference between those and electronegativity is that electronegativity is within a bond. The others were just ions. So electronegativity increases in the same way that the others did. It increases in this way and this way, except for the noble gases. The noble gases are excluded because they are not interested in making bonds. So fluorine, again, not a to scale periodic table, but fluorine would be the most electronegative element. Okay, so let's look at some examples. So let's look at hydrogen versus hydrogen fluoride. So here's hydrogen up here. So hydrogen has a very low electronegativity compared to fluorine. So let's look at hydrogen. Remember, hydrogen is diatomic. So when I say the word hydrogen, it's H2 versus hydrogen fluoride. HF. Okay, so remember hydrogen and fluorine are both nonmetals, even though hydrogen is over here. It doesn't really belong anywhere, but nonmetal, these are both covalent molecules. So electronegativity, so we're sharing the electrons. Hydrogen is sharing the electrons with hydrogen. Hydrogen is sharing the electrons with fluorine. So let's just draw both of these. So this would be the Lewis structure for hydrogen, because there's 2 electrons. I'm sharing these 2 electrons. And then this would be the Lewis structure for hydrogen fluoride. I have 8 electrons, 7 from the fluorine, 1 from the hydrogen, 2, 4, 6, 8. Everybody's happy. 2 for the hydrogen, 8 for the fluorine. Okay, so let's see what's happening here. These are both covalent bonds. This is a covalent bond. And if we were to pretend that these circles around here were the electrons, and the electrons are orbiting the hydrogens, they're orbiting these 2 hydrogens equally. The electrons are orbiting these 2 hydrogens equally because these 2 hydrogens have equal electronegativities. Because they're the same element. So the electrons that are orbiting this hydrogen molecule are equally attracted to both hydrogens. Equal electronegativities. You could also say equal sharing of electrons. So now let's look over here. Hydrogen and fluorine. Well, hydrogen has a very low electronegativity compared to fluorine. These are unequal electronegativities. And we are going to have unequal sharing of electrons. So the electrons that are being shared here in this bond, they are going to be way more attracted to this fluorine than they are to this hydrogen over here, which just has such a lower electronegativity. The electron is going to spend way more time around the fluorine because the fluorine is so much more electronegative. So we call this equal sharing versus unequal sharing polarity. So polarity has to do with the sharing of electrons. So if you have equal sharing, this is called a non polar bond. It's non-polar. You think of the word polarity, think about like the North and South Pole. They're opposites. So if you're polar, you have two very different regions of electronegativity. This is a non-polar bond because we have equal electronegativities. This would be called a polar bond because we have two very different regions of electronegativity. The fluorine is very electronegative. The hydrogen is not electronegative. The way that we represent this is by drawing a vector, or sometimes it's called a dipole moment, where we draw an arrow. The arrow points towards the more electronegative element, and then this other end we put a cross here, which kind of represents the less electronegative element. So this is called a vector, this arrow. It's also called that this has a dipole moment. Polar bonds have dipole moments. Non-polar bonds have no dipole moment. There's no vector here because there's no separation of charge. It's equal attraction to the electron. Here there is a separation of charge, so we have this vector. This we also can represent with the lowercase Greek letter delta. So this would be the more electronegative side. This would be the less electronegative side. So if you were looking at this molecule overall, this side of the molecule would be more electronegative because it would have more electrons. This side of the molecule would be less electronegative, more positive, because it would have less electrons. So this polarity is going to be really important when we start talking about molecules and shapes of molecules in Chapter 5. But this is polarity in a bond. If you have differing electronegativities, that is a polar bond. If you have similar electronegativities, that is a nonpolar bond. So there's actually values for which you can determine if a bond is polar or not. And you would be provided a chart that would tell you how to determine if a bond is polar or not. Let me just find where that is for you in your textbook. So it's on page 153 in your textbook. And what it shows you are all of the electronegativities. And the difference between the electronegativities tells you if the bond is polar or not. So usually a difference of 0.4 or greater represents a polar bond. So this is what your textbook says. So if the difference in electronegativity is greater than or equal to 0.4, we call that non-polar covalent. These are all covalent. If it is, so I'm just going to say the electronegativity, I'm just going to call it X, whatever those values are. If it's between 0.4 and 2, it is polar covalent. And if it is greater than 2, then it's ionic. So again, you would use these values in the table on page 153 to determine if something was polar or not. So for example, we had hydrogen and fluorine. So the difference in the electronegativities here, hydrogen has an electronegativity of 2.1, fluorine is 4.0, so the difference here is 1.9. 1.9 is between 0.4 and 2, so that means this is polar. Here, the electronegativities are 2.1 and 2.1. The difference is 0. If it's less than 0.4, it's considered nonpolar covalent. So you would be provided a chart, or you would use your textbook when you're doing your SmartWorks homework, if you're being asked to determine if a bond is polar or nonpolar. So that is electronegativity. It's the ability of an atom to draw an electron to itself within a bond. This is the important part. This is what differentiates it from electron affinity and ionization energy that we covered at the end of chapter 3.